For in high-performance computing applications, bulk tier-2 data storage systems can amount to several petabytes of data and are built on the largest disks. However, the main problem is the slow recovery rate in case of disk failure, which can take days to rebuild and carries the risk of additional failure and data loss. Our next presenter is Sergey Platanov, VP of Strategy at Xinnor, who's been involved in developing high-performance storage for 14 years. Today, he will discuss a method that reduces the recovery time to a few hours using declustered RAID technology and optimized block allocation maps. Sergey, how are you today? Welcome to the conference.
Thanks, I'm very good, thank you. However, it's almost late night here. We are based in Haifa, Israel, so I hope my followers are not going to interrupt me. Anyway, I want to excuse in advance, just in case. So, and let's go. So we are young data storage company from Haifa, Israel, and thanks Brian and the team for great opportunity to speak today. And I'm going to talk about our research on storage optimization for multi-petabyte parallel file system deployments. And as a company doing something for storage, we had the idea to focus here to performance tier, doing software for NVMe, storage class memory, GPUs, but fortunately or unfortunately, I don't know, our partners want us to adopt our technologies for capacity tier and nearline storage to have all the storage layers from single hands, and we had to change our mind and do something here for multi-petabyte storage systems where high performance is still required. So here are some simplified Lustre and BGFS architectures, and very often they rely on the use of RAID, local or external, and large datasets require special attention to fault tolerance for two main reasons. The first one, a failure of drive or node can be extremely costly in terms of amount of data lost or computational time wasted, and wrong handle of failures can slow down the entire file system cluster. So what's wrong with existing high availability approach? And so most of available approaches require a significant over provisioning of resources if we want to achieve the required levels of performance. And data mirroring is very expensive for large storage volume, especially when we're using QLC, NAND flash. And we know about some work on using erasure coding on client, but this work is far from production ready solution. And typical 1+1 cluster in case of failure of single node requires to move storage services to paired node, and in this case performance drops by 50%, or customers need to provision hardware for such cases. And simplified pictures, you can see here simplified pictures. In case of not free failure, you need to move IO operation to node 2, and to save performance levels, you need to have double capacity of SAS links, of network links, and double capacity of memory, etc. And I'm going to say more about how long it takes the RAID array to rebuild. Okay, and we see continuous investment in increasing storage capacity by drive manufacturers. Today we have a 26 terabyte hard drives, and the largest flash drive I've seen is 100 terabytes drive from Nimbus Data, and at 1 or 200 megabytes per second recovery speed per single drive. Rebuild of hard drive rate takes from 35 to 70 hours, and for when we're talking about QLC based RAID rebuild can be from a few hours up to 2 days. So there are a couple of ways to improve RAID rebuild performance, and 1+1 clustering. The first way is method called declustered RAID, and I will discuss about declustered RAID today. And this technology is available from both major storage vendors, very popular in high performance cluster deployment. And you can see declustered RAID as a part of open source solution like ZFS. And the second way to improve data availability is storage disaggregation, which allows us to move resources from one server to another very quickly, and it gives us the ability to build N+M and N+1 clusters to distribute the load efficiently across all the nodes in case of single node failure. So what is declustered RAID? Suppose we have a classic RAID 50 of 16 drives and consists of 4 groups of 4 drives each. So we have 4 groups, group A, B, and C, and D. And in case of drive number 5 failure, we need to replace drive or wait for spare drive connected to the RAID group, and recovery time is limited by the write performance of new drive, and only disk from group B is included in recovery process. And this makes RAID rebuild very slow. So declustered RAID, the main idea is to shuffle the location of data chunks and parity chunks across all the drives, and also we leave free spaces within array where data recovery will take place. So S means free space to recover the data. So once again, in case of drive number 5 failure, we restore data to multiple empty zones, and we are not limited with performance of single drives, and all the drives from RAID 50 precipitate evenly in recovery process. And this theoretically allow us to a significant increase the rebuild speed. So, and a lot of companies use feature-rich ZFS as a solution to their storage stacks, and this product constantly evolving, and not long ago it was declustered RAID added, and soon direct.io initiative will boost performance significantly, and of course we are considering ZFS as a part of our solution. And we did some research, and first and foremost we look at performance, and we have performed test on a simple building block consisting of 60 drive JBOD connected to single server with 4 SAS 12G paths, and we perform testing using flexible IO tester by increasing a number of files, and also we compare the performance of file system with direct.io on and off. So unfortunately, ZFS, on which we have almost all functionality disabled, does not allow us to get the most out of the drives. So you can see with the maximum performance, total performance of drives at almost 13 gigabytes per second, we got only 5.2 gigabytes per second from file system. Using direct.io, we can squeeze out not bad results under very hollow. I mean here about 500 writing jobs. We were able to get almost 7 gigabytes per second here, but latency was quite high, and results was really unstable. And as we see, ZFS DRAID with double parity is very inefficient in case of small number of files or writing jobs. It's demonstrates the performance of 10 drives, not of 16 drives here. And we decided to redevelop RAID engine, and we developed our own RAID engine, which can replace RAID-Z and DRAID in ZFS and still performs much better. And it based on very simple ideas, or like lockless IO handling, very effective RAID calc specialization with AVX and AVX2, and we use the shortest data path as possible. We don't use any device mapper framework, etc. And we have doubled the performance of file system. Unfortunately, you can see that as write load grows, it starts to lose a bit of performance. But we are fixing that right now, and we are going to demonstrate about 90% of maximum portable performance from existing hardware. And the second important part for us is data recovery rate. And as I said, ZFS had DRAID, which is optimized for large data sets, declustered rate, and we measured recovery performance. And the idea was to fill the file system and run recovery process with no additional load. And we ran tests several times and finally compared it with a classical RAID Z2 rebuild performance. So RAID Z2 is simple double parity RAID. First attempt was quite good. We increased performance 4 times, but the second and third attempt didn't show the same result, and results are very different from run to run. We did almost couple of dozens of tests, and each time we saw different results, and we understand the reason. DRAID uses the random chunk allocation map, and for hard drives, we can't read and write to more than a single area of drive at the same time, and that's why we can guarantee full parallel recovery in case of random allocation map. So the example shows that stripes of the same color can be recovered at the same time. For example, stripes 2 and 4 can be recovered at the same time because they don't use the same drive recovering data, but stripes O and stripe 4 can't be recovered at the same time because they use, for example, both of stripes use drive number 7 to recover, drive number 1 to recover, etc. So that's the main reason why we can't guarantee the maximum possible performance when we have random map of data placement. So once again, we decided to recreate the existing solution, and we developed a range of near perfect chunk maps for different types of drive failures. Perfect map is obtained when the number of data groups within which we can recover all the stripes in the same time is equal to the number of RAID subsets. So, for example, if we have RAID 50 with 4 groups of 5 drives, we should have 4 groups of stripes with the same colors to get the maximum possible performance of recovery. And so we developed different maps for different RAID sets. And here you can see the performance improvement over legacy approach. So at the base case, we improve for existing approach with more than 10 times. So we still have a very long way to go. We want to optimize our algorithms for SMR and zoned flash devices. And in case we can write to zones randomly, we should adopt our chunk maps for size of RAID zones. Also, we are working a lot on storage disaggregation, even for closed C drives and for hard drives. And we are happy to cooperate with any companies who are really interested in optimizing some existing solutions like ZFS, like cluster and BGFS, and we're constantly looking how we can optimize it using some mass research and maybe some knowledge in how Linux kernel operates with storage, with I/O, and etc. So I'm almost done. I have a couple of slides describing, for example, ZFS setting. If you're interested in how did we say we tune ZFS, so we switch off almost all functions, and we have had record size equal with I/O size. We disable compression, duplication, time, and checksums, and even in this case, we didn't get the maximum possible performance of storage. That's why we decided to recreate RAID engine for ZFS, for BGFS and cluster. And also we did some optimization for ZFS block model, mostly improving ZFS with def parameters. So I'm done and happy to answer your question if you have.
Thank you, Sergey. I currently don't have any questions in the queue. Let me just give it a little moment to see if anyone is writing something. Don't see anything yet, but if you want to hang on for, a bit and see if anything kind of comes in that you can answer via chat, then that would be fantastic. Sergey Platanov, everyone. Thank you so much.
Thank you.